Hello, everyone, and welcome to this talk. My name is Josephus, and I'm the core team leader of the NUbots team, along with Isabel Sims. We're both final year Bachelor of Computer Science students at the University of Newcastle in Australia, where the NUbots team is based. Today, I'll be talking about NUsight, specifically sharing some of the lessons we've learned while trying to build a robust and effective debugging tool for soccer playing robots. So for the past several years, the NUbots team has been building and using a visual debugging tool, and this tool we call NUsight, which is a collection of related smaller tools that provide real-time visualization of both low-level and high-level data from a robot. It includes a dashboard, a 3D localization view, a vision view, as well as a chart view. More on these later. So NUsight itself is web-based. We chose the web because it is cross-platform, and we have people on our teams that are using Linux, some people are using Windows, others Mac OS. So choosing the web allows us to run the tool on any platform. And we also chose the web because it's designed for presenting information, and it has multiple rendering APIs that we can take advantage of, including 3D APIs. It also has a short code debug loop, which is very important for rapid iteration when you're building a tool like this. So you make a change and you see it as soon as possible. NUsight has a many robots to many clients architecture, where any number of robots can connect to a single NUsight client via a server that sits in the middle and relays messages between robots and the NUsight client in the browser. We found this is very useful. We found, for example, at RoboCup, since it allows us to debug multiple robots at once using a single computer, as well as using different computers to debug different robots. We found NUsight to be very useful in the development process, as it allows us to use our natural intuition to debug issues visually, as opposed to thinking about raw numbers and trying to do maths in our head to figure out what the numbers mean. For the rest of this talk, I will be sharing some of the things we've learned while developing two major versions of NUsight over the past several years. And hopefully you can walk away with a tip or two that you can apply when developing your own debugging tool. But first, let's talk about what makes up a debugging tool like NUsight. The first thing you have is data. These are the raw images and raw values you want to visualize. It could be sensor readings on a robot, servo positions, camera images, vision objects, etc. Next, you have networking. This is how you get data from a robot into the tool for visualization. So this includes your transport protocol as well as the data format that you use. On NUbots, we use a UDP-based messaging system with protobuf messages. The final piece is rendering, which involves displaying the data in the user interface and providing interactive controls for the user to interact with the visualizations. Through the process of designing and building NUsight, we found 5 key principles that help us make a robust and effective system for debugging. And these are: keep it simple and straightforward, use UDP with stateless messages wherever possible, use declarative data-driven rendering, go beyond just numbers and graphs, so think about new ways to visualize data that are more intuitive, and give users control over what is visualized. So we're gonna take a closer look at each of these, starting with the first one, which is just keep it simple and straightforward as possible. This is very common coding advice. And the reason it's important is, in this context, is when you're debugging an issue, you don't want to be guessing if it's the system you're debugging that has the problem, or if it's the debugging tool that is incorrectly displaying the information. Because when this happens, it can lead to the situation where one person thinks it's the system that is at fault, and then another person thinks it's the debugger that is at fault. And then you end up arguing back and forth without actually getting to the root of the situation. On the NUbots team, we have a saying, it's never NUsight's fault, which is not always true, but we try to build a system such that most of the time, if there is a conflict between the NUbots system and NUsight, we can be confident that the problem is not in NUsight. So how do you keep a tool simple? The first thing you can do is to minimize the number of settings and configuration. So the NUsight itself has 0 configuration options. It's just start and go. So every time you need to make adjustments or control the UI, it happens in context. So using a drop-down menu or some sort of button closest to where that setting is going to have an effect. The next thing we do to try and keep it simple is to look at NUsight as a viewer. So only responsible for displaying data. So it can only display whatever it receives from the robot. So there are no simulations in the tool or making predictions about the data. The only thing it displays are the things it receives. Another way we try to keep it simple is by adopting certain design patterns and principles that exclude an entire class of bugs, some of which we're going to talk about next. One of these is using UDP with stateless messages. To see what I mean, let's consider TCP versus UDP. So in our case, we prefer to use UDP over TCP because if the network performance is poor, which is something that happens at RoboCup, TCP can make it worse when it tries to ensure delivery. So if you send packets that fail to arrive at the destination, it'll keep trying to send those packets until they do. This leads to a lot of latency, which can be bad for a real-time debugging tool, such as NUsight. But if you choose to use UDP, it's not reliable, so it doesn't ensure that your messages get there. So you may lose packets during transmission. So the way to get around that is to use stateless messaging. So practically, this means you don't send data in parts. So each message should be self-contained, having all the information you need to visualize it. This may be less efficient since you're sending very similar data in each packet, but it avoids the problem of holding on to partial state, which you may not get the next part of the message to be able to render. As an example of this, we send a vision image message to NUsight. And when we send this message, we also include everything NUsight needs to render the message. So we don't send it in multiple parts. The first thing is the data, which is the actual image itself. Then we send through the transformation matrices, as well as the camera lens. So any information that NUsight needs to render, we put it all in here, so the message itself is stateless. It doesn't have to wait on extra information. Another key principle that we use is wherever we can, trying to use declarative rendering that is driven by data. So what do we mean by declarative rendering? And how does it compare to other ways of rendering, like imperative rendering, for example? With declarative, you just specify what you want and you let someone else, usually a platform or library, figure out how to render it. So SVG is an example of a declarative rendering API. With SVG, if you want to draw a rectangle, you tell the system you want a rectangle. You specify a width, height, fill color, and the system takes that information and figures out what is necessary, all the steps involved in drawing a rectangle. With an imperative API, like the Canvas 2D API in browsers, you know what you want, but you also have to specify step by step how to render it. So if you wanted to draw a rectangle, you have to create a canvas, and then you get a reference to that canvas, get its 2D context, set your fill style, and then finally draw your rectangle. As you can see, one of these approaches has a lot more code than the other. And the more code you have, the bigger the surface area and the higher the possibility that you're going to introduce bugs. So in NUsight, we try to default to declarative rendering wherever possible. So we start with SVG. The dashboard view, for example, is all SVG. So when we run into problems and performance issues with SVG, when we want to render a 3D scene, we switch to either Canvas 2D or WebGL. These are both imperative rendering APIs, so we wrap them with a declarative layer on top. This layer takes the data we want to render and it translates it into a set of imperative calls for the given backend. The advantage to this approach is that we can write and test this translation once, and if it works, we can be sure it'll work in the future without the need for any changes. So next we have data-driven rendering. So we've talked about declarative rendering. So with data-driven rendering, you try to model your UI as a function of state. which is the data that you want to render. With this approach combined with the declarative approach, all you need to keep track of is the data that you want to render. And as soon as that data changes, say from user input or something coming from the network, the UI will be automatically updated to reflect the change without any effort on your part. To do this in NUsight, we use React, which is a declarative UI rendering library. And we combine it with MobX, which is a library that manages state and efficiently re-renders the UI automatically when data changes. So if you have a big scene that you're rendering and only a small part of that scene changes based on the data, MobX is going to figure out the minimum amount of work to update the UI in combination with React. The next principle is going beyond raw numbers and graphs. So thinking about new ways to visualize data that are more intuitive for people to understand, especially in the context of RoboCup, where everyone is sleep deprived and lots of stress. You don't want people thinking about things they shouldn't be thinking about. And there are lots of ways to do this. But one of the key ideas behind most of these approaches is to make visualizations that look like the real world. For example, in NUsight, our localization view shows the robots in 3D with their location on the field, orientation, and servo positions all reflected in real time. This is very useful for debugging motion and localization issues. So you can take a robot, move its arms around, and you see it moving in the 3D view. If something is wrong with the motion and it's not being reflected in NUsight, you know where to go. So you might have a look at the servo or see something in the motion code. For another example, we have a vision view in NUsight which shows the camera images directly from the robot with detected objects and points of interest overlaid in real time. So we can look at this and see exactly what the robot is seeing. Is it detecting balls? Where does it think the goalposts are? The field boundaries, things like that. Again, very useful for debugging vision when things go wrong. Another key idea is to visualize data with the information about the system and the surrounding context where appropriate. For example, in NUsight, the dashboard view shows an overview of the robots when they're playing a game. By the way, this is simulated data from virtual robots. The view shows each robot where they think the ball is, that's the orange dot, and what their current walk path is, that's the black curve, the arc. The sidebar also provides context and system information by showing the connection status, battery level, current game state, walk commands, where it's going to go next. Usually that is at the bottom of the field because we have multiple robots and you can see them all at a glance without needing to click or do anything. You also notice, again, going beyond the idea of just showing numbers. So at the right, there is the walk command, which is just a coordinate. But we visualize that also with this arc, which shows you where the robot is going to go from where it is. That makes it easier to see as opposed to thinking about this number in your head. The final principle is about giving the user control of the tool and control over what is visualized. So this can be applied in two places. The first is where the data comes in, so at the input layer. For example, in our main code base that runs on the robots, we have a configuration file for NUsight. This is a YAML file that provides a simple way to control exactly what data is sent to NUsight from the robot, allowing the user to pick and choose what they want to send. For example, you can disable vision objects. If you don't want the detected vision objects to be sent, you set it to false. We also have the ability to emit data to NUsight from any part of the system using a global function. So that makes it really easy if you are working on a very low-level feature and you want to chart the values you're getting in NUsight. You just emit those packets, and NUsight receives it and displays it on the chart for you. So these are two places where you can give the user control over what goes in. Another place to give users control is when the data comes out, so where it's visualized. We do this in a number of places in NUsight, one of which is the chart view. So here on the right, we have a checkbox tree that shows every robot that is connected to NUsight, as well as all of the data that they're sending. So the user has control over exactly what data points are plotted from which robots. and they can change the color of any of the lines on the chart for easier identification. And they can drill into specific data points. So if you want to show, for example, if you think there's something wrong with the right shoulder pitch, you can just plot the values that you want from that data packet, and it's all shown on the left. So in conclusion, we found that a real-time visual debugging tool such as NUsight is very useful and improves development efficiency when you're building complex systems like we do with these soccer playing robots. So it's very important to recap, to keep it simple, use UDP with stateless networking where possible, use declarative data-driven rendering. So if you're working on the web, libraries like React and MobX are very good. Go beyond numbers and graphs, so think of new ways to visualize data and show it to users that's more intuitive and quicker to understand. And also give users control over what is being visualized, both at the point when it's input into the system and when it's rendered. So just want to say thanks to Brendan Annable. I think he's attending this presentation. He's the creator of NUsight, and Trent Holliston, who is a contributor to NUsight, as well as the rest of the NUbots team for their help in preparing this presentation. I think they're both here, and they'll be happy to answer any questions you might have along with me. So NUsight is open source and available on GitHub at this URL. You can use it as a reference when you're building your own debugging tool, or you can fork it and start there. We're also happy to answer any questions you may have. You just email us at that link. We're also here now to answer questions or later in the Discord. Thank you. So more than happy to answer any questions about NUsight, NUbots, the way we connect the two systems.
I'm sorry, can I just ask a question? I just can't find the button to raise the hand. Seems.
Yep, go on.
Yes, so I have a couple of questions. So one question is, well, we're using Java to program our debugging tool and all, right? So, but you talked about that you prefer UDP. And we thought about this a lot as well. And so we are using TCP. And so one of the things that prevents us from easily switching to UDP is the images. How do you deal with those? Because they don't fit in one UDP package, I think.
Okay. Yep. Trent, would you like to take that?
Sorry?
Sure. Sorry. Well, you're right. They don't fit in one UDP packet because you've got the MTU of about, I don't know, 1,500 bytes, and then you've got the maximum limit of 65535. So we have to actually split them up. So we have we don't just use raw UDP to send messages. We actually have a messaging layer over the top of that handles splitting packets up into multiple messages and sending them and reassembling them at the other end. But because we're using UDP for that and not TCP, we're not relying on the order of arrival. So when we send messages, just say that we were trying to send an image, but the bandwidth was really, really low. And those packets were constantly dropping and we were having trouble sending all of the packets required to assemble the image on the other end. And then we wanted to send, say, a sensors packet, which has, IMU and servo data in it. That packet, which is small, can still get through to the other end. Whereas with TCP, it would continuously keep trying to resend those same image packets, and those sensor packets would sort of build up after them because it has to send them in order. And you would never get the sensor data just because it kept failing to send the image. So using UDP in that way, we found it much better. We do have to do a little bit of logic to take the packet, split it into a couple of hundred UDP packets, and then send them all across the network.
Ludovic had
Okay,
a
so
comment.
a quick comment from the TC point of view for the UDP TCP problem. Well, anyway, TCP is forbidden in the league because it means that your monitoring computer will send packets to the network, which is forbidden in Humanoid League. So this means that all monitoring during games has to be done by UDP. So that's also a strong point for UDP.
Oh yeah, well, to make it clear, I mean, we are using UDP for team messages and monitoring during the game, obviously, right? So, but we use TCP for, you know, we debug with cable and so on. I also wouldn't, I think, send images through during the game, I guess.
I
So,
don't think you could.
yeah, but thank you for clarification. That's very interesting. And another question I would have is that, like recently, I came across the visualization library by Ross. Is it like a WebKit or something like this, right? So, which looks quite comprehensive. Have you looked at that?
No, on our team, we don't use Rust. So we haven't been looking into any new visualization systems that they're coming up with. But it sounds like it might be something interesting to have a look at to see how they're doing, how they're solving some of the same problems, and find ideas that we can use to improve our own tool.
Yeah, well, and I think, so my impression was, I don't have any details right now, but like my impression was that this library was actually independent of Rust. So it's more like, so using this, but it's available for them.
Right. Right. So it's more of an integrated solution. It's built into Rust itself. Yeah, so our system is independent. So NUsight works separate from NUbots. So the robots don't run any NUsight code at all. They just send out packets, and NUsight is on another computer listening for these packets and visualizing them. So they're not integrated. Any other questions? Heinrich just shared the link. So it's called RoboCup Web Tools, collection of open source modules and tools for building web-based robot. Oh, so it's also web-based, just like NUsight.
Yeah. So that's what I thought. It was very interesting because it reminded me of what you were presenting, and it seems to be sort of independent of Rust, you know. So, but I'm not sure. I haven't tried that, so I can't recommend it. I was just, you know, dropping in a link I found.
Definitely, it seems like something that is worth looking at least. By the way, I'm not able to see participants, so I'm not sure if anyone has their hands up.
Not at the moment. Ludovic has another question.
Yep, so that's only the problem for all the co-hosts and hosts. We cannot raise our hand. I don't know why this is implemented this way, but that's why you were not able to find the button, Heinrich. But my question is not about that. My question is more about, like, you have everything which is kind of generic, for example, for the graphs.
Mm-hmm.
But what happens when there are something which are not suited for this genericity? For example, when you have several different data to plot, and they are not at the same scale at all, is there an option to split the graph, for example, or something like this? Because that's always a problem I tend to have when writing monitoring interface for the robots, is when you try to apply the KISS principle, then often you're saying, oh, I would like to have this, this is really important, but this is making everything more complex.
At the moment, we plot all the data on the same scale. It's something we've thought of before, coming up with multiple charts to have that at different scales. But at the moment, the best way we would do that, I think, would be to make another chart view that is specific to that type of data that we want to plot. If that makes sense.
Okay, yeah.
Yeah.
And for extending the tools, well, for example, you have a new variable you want to send with your message. I think it's easy to extend the protocol with protobuf. But what if you want to add something you want to draw and it does not fit with the basic tools you have? Might it be complex to implement or not?
In this case, because it's the same team that builds both the NUbots side and the NUsight, we usually just update the visualizers that we have when we have new data to visualize. And that involves just going into the code for NUsight and changing the way it does the visualization, so it takes into account any new information we have on those messages.
Since the tool is declared in a declarative way, what it means is when we want to draw a new object or a new different data type or point, we just need to declare how we want that drawn and which data it depends on. And it's quite easy to add new functionality. That's one of the things we were very careful to write, is that we wanted to make it really easy to add new functionality, because as you know, like when you're developing robotics, you often just want some particular visualization, now. And if it's too hard to build, you'll just go and plot out raw numbers and then throw them in Excel and play with them until they are what you want, which is much less ideal than debugging in real time.